gravity in numerical relativity, and it will be given by Helvi Witek. Helvi is an associate professor in the Illinois Urbana-Champaign, and she's an expert on alternative theories of gravity within the numerical relativity framework. So I'll let you know when you have 5 minutes left before the questions, and you can start whenever you are ready.
Okay, thank you so much. And also thank you for organizing the European Einstein Toolkit workshop this year online and for inviting me. Let me try sharing my screen first and make sure that the slides all work. And okay, this is one. Let me get rid of the video panel and the floating controls, which means can you check? Yes, continue to share.
Yes, it works. Yes, it works. Thank you.
Okay, and could you also check the chat and everything and give me the time as needed?
Okay.
Very good. Excellent. So thank you so much for having me here and inviting me to talk about numerical relativity. I know the original title is in modified gravity. I wanted to extend that a little bit and talk about some applications of numerical relativity more broadly in fundamental physics. And I will focus on applications and simulations done with the Einstein Toolkit, and some of them, or most of them, with our in-house code, which is called Canuda. And I saw that my talk is one of the very few who goes outside standard general relativity or neutron stars. So let me actually start with a brief summary of applications in fundamental physics. So what you've already heard quite a bit is gravitational wave modeling for binary black holes. This is a snapshot here from Deborah Ferguson's simulation that she did in my group when she was a postdoc here. And of course, we have a large number of absolutely amazing talks on neutron star mergers and phenomenology and simulations. But going beyond that, we can think about testing gravity, thinking about whether Einstein's theory really describes gravity at all scales. And there are really nice works on black holes and some neutron stars in specific extensions of general relativity. There are questions about extra fields, dark matter, and there is a large class of dark matter candidates that we can actually probe for with black holes. There are questions of whether or not the compact objects that we are seeing are indeed black holes, or could they be boson stars or microstate geometries. And I believe Steve Liebling is going to talk about some of that later on today. There is a large body of work on cosmology, where you can really tackle new problems with strong gravity in numerical relativity. I believe there's a really nice Living Year Review article by Yuzo Auracocha, Katie Clough, and Eugene Lim. Early work is going outside gravity in 4 dimensions. And for today, I want to focus on some modified gravity in the end of the talk and some applications for probing for new fields in the middle of the talk. Okay, one more disclaimer. I think most of what I will be talking about today is work done in my group, which you can see here. So this is one of our most recent photo from October, and I will present most of their work. Good. So with that, what are we going to go through today, talk about today is our software that we have here in Illinois, or co-developed in Illinois, for applications of numerical relativity and fundamental physics, thinking mostly about these new types of particles, new types of fields, and extensions of general relativity. And I will talk about these 2 applications here. 2 disclaimers, because there's a lot of really interesting work and a lot of new results in the last 5-6 years. So I really just present some highlights. And as I said, a selection focusing on work done with the Einstein Toolkit and with Canuda. And I will talk mostly about black holes. I think I have one animation on neutron stars, but everything else will be about black holes. Good. So let's jump in. Let's talk about Canuda. This is a busy slide. But as an upshot, our software Canuda is an extension or an add-on for the Einstein Toolkit. And it's really co-developed not only by my group, but also was conceived of by Miguel Zayao in Portugal. And in recent years, Nico Sanchez-Gual in Valencia has also contributed to the code, and our postdocs and graduate students. If you want to find our Bitbucket repository, you can follow the QR code, and it's also linked to the Nodo. So in the bottom of the slide, you see a lot of pretty pictures. These are some applications going from these black holes plus extra fields in dark matter environment, which you will see more of later. You already noticed or saw the black hole simulations in modified gravity. We also recently put a paper out on scattering black holes just in general relativity, and Freddy Pardo will give a talk tomorrow. And we have some applications here from the group in Portugal and in Valencia. And if you have used our code and you don't see your picture here, please let us know, and I'm happy to showcase your work as well. Good. So how is Canuda structured if you wanted to use our code to do simulations outside standard vacuum GR or neutron stars? We have a number of arrangements. If you're not familiar with the Einstein Toolkit language, arrangements is essentially a collection of individual sorns, and each of these sorns has a specific task. So for example, there are sorns that will define just your grid functions and their symmetries on the grid. There are sorns that will provide the initial data, and there are sorns that will do the evolution, and other sorns doing the analysis and output. So a lot of the infrastructure we are using from the Einstein Toolkit. So really Canuda is an add-on where we have one arrangement that's called Lean Public, based off an older code developed by Oli Sperhake, but really rewritten for Einstein Toolkit, where we provide the space-time evolution within just general relativity in currently the BSSN formulation. We have analytic initial data for care, for example, in quasi-isotropic coordinates, and we provide wave extraction using Newman-Penrose scalars as a complementary implementation to the Einstein Toolkit standard, say, Weil scalars. And asterisk here means this is in the official release of the Einstein Toolkit. So that's when you download the toolkit, you will already have that arrangement. Another one that we already have is for scalar fields, where we can evolve complex scalar fields that are coupled to general relativity. This includes both constraint satisfying initial data, and I will go through this later on in the talk, and evolution. Similarly, we have an arrangement for Broca fields. Broca fields are massive vector fields that are interesting as potentially dark matter candidates, but in the limit where this extra mass goes to zero, we actually also just reduce to Maxwell's equations. So we have that in as well. Then we have two big arrangements for simulations in modified gravity. And I will point out this one later on called Axi-Dilaton, where you really have a generalization of general relativity to include additional fields and higher curvature terms that you can then select models. You can select the model that you want to do and to evolve by just setting a parameter. And the latest developments are on Canuda X standing for exascale computing, and is working together with Carpet X, where we already have space-time evolution, initial data, and wave extraction within general relativity. And I wanted to showcase a few examples of that as well. And I should say, I know you already had quite a few talks and tutorials earlier this week. This endeavor is really led by Eric Schnetter and Roland Haas, and we are working together with PIs, Steve Brandt, Pablo Laguna, Zeki Tien, Josef Slokova, and I think in Europe, Philip Muster, and their respective teams on new development. And Carpet X provides GPU support, and it seems that initial benchmark tests really show a much better scaling than you find with standard CPU simulations. So the work towards that in our group here is called Canuda X. And as I just said, we have space-time evolution with BSSN in the BSSN formulation and moving puncture gauges. We have exact initial data. Carpet X already provides binary black hole initial data through a translation of two punctures, and we have wave extraction. One of my students, Nora Gadiri, is also porting the exporter to use Spectre's Cauchy characteristic extraction to CarpetX, so that should become available in the next few months. Otherwise, our development here in Illinois is really led by Cheng. You can see here, he's applying for postdoc. So if you're interested in getting an expert on CarpetX code development and GPU computing, here is your person, he's your guy. And new in the team is Jay Kalinani as a postdoc, and he has also done absolutely fantastic work interfacing neutron star simulations with our infrastructure, and of course going way beyond that and working on the neutrino transport schemes. So examples that we are seeing down here, let me start with the left-hand side picture, where you see a simulation of a binary black hole, QC0 run. So they're really starting at a separation of just a couple of m in spiraling. And let me just start playing this because it goes a while. So on the left-hand side, you're seeing the grid structure and how it evolves using CarpetX. And on the right-hand side, the color coding indicates the Newman-Penrose scalar, so the gravitational radiation emitted by this coalescing binary. In the middle is some work from Lucas Sanchez, who shared with me his evolution of a scalar wave in CarpetX, which is a multipatch SORN, and you can see a wonderful example here. I believe Lucas talked about binary evolutions using CarpetX a couple of days ago. So this simulation was 2 months old. I think the latest results are also really exciting, and I'm happy that he could share this with you. And then the last animation here on the right is showing the coalescence of magnetized neutron stars that Jay shared with me. So this is the first binary neutron star merger simulation that he conducted with AsterX. Okay, so let's just finish the simulation. It's really exciting to see all this development and success going on there. It's really productive and exciting to see that these simulations work and we can start doing science with them. Okay, so that was all I wanted to share about our code, Canuda and CanudaX. So let's go to the first application where we want to think about black holes and additional fields. And if I say additional fields, I'm mostly thinking about scalar or vector fields. And they're interesting for two very different reasons. On the one hand, you can think about having these extra fields to perturb your black hole. And then you can ask, well, are my black holes stable if I perturb them with a scalar or a vector field, especially when these fields have a mass? Because it's known already from literature, from perturbation theory calculations, that a massive scalar field and a massive vector field can lead what's called a superradiant instability. If the fields are complex, you can actually form really black hole hairs that circumvent standard no-hair theorem. So there's a lot of interest in this from the theoretical perspective. But then at the same time, these additional light scalar or vector fields have a mass that is interesting in the context of particle physics beyond the standard model and dark matter particle physics. And this is one of the, at least for me, one of the biggest questions, I think, in fundamental physics, because we have observations that indicate that more than 80% of all matter that gravitates is dark matter. So it's something that we don't understand. The stardust that we are all made of is maybe somewhere around 20% of all the matter in the universe that's gravitating. And one of the observations that I'm showing you up here is a lensing image where light from a faraway galaxy is lensed through the gravitational field in between, and we get the universe to smile at us. Now, the dark matter problem is not an easy one, and in fact, if you talk to particle physicists, they will give you answers and ideas of what dark matter could be that range over 80 orders of magnitude in the mass range, going from somewhere in micro and electron volts and even lower, all the way to the mass of the sun and more. And this comic here from XKCD suggests maybe it's space cows, maybe it's some buskil astronomer. I'm afraid it's not that. But what we can do with black holes is actually probe for a range of these candidates that are called axions, which are very light scalar particles, or what sometimes is called a dark photon. So these are very light vector type particles, or the Broca fields that I mentioned earlier. Okay, so what mass range are we talking about? And we will see that in a second. But let me first write down the action in the Lagrangian that we are thinking about. So here we will have our Einstein-Hilbert term. Then we couple to that a massive scalar field. This is just the kinetic term of the scalar field phi. This is the mass term of the scalar field phi. And then for the massive vector field, the Broca field, we again have just standard field strength. So this is kind of the kinetic term for the vector field, and this is the mass term. And then what has already been shown is that you can form a cloud of these bosons, these massive scalars or massive vector fields around a black hole, either through the superradiant instability that I mentioned earlier or through accretion. Now we can talk about the mass range. When does this happen? And that happens when the ratio between the black hole radius, so the Schwarzschild radius here, compared to the Compton wavelengths of the field is of order 1 or 1/2. I can translate that into the mass of the black hole, capital M, and this mass parameter of the fields, and what I get if so I should say this looks maybe a little bit weird. Why mass times mass? I'm using here natural units. So speed of light is 1, Newton's constant is 1, and h bar is 1. And this is what you get. And if I reinstate the constants and the appropriate units, the number is 10 to the 10 mass of the black hole in solar masses and a mass energy. And I can translate this. So what kind of particles can I probe with the astrophysical black holes that we know about in the universe? Let's take a black hole of, say, 50 solar masses. So this is in the range of black holes that we can observe with ground-based gravitational wave detectors. And we could probe additional fields with masses in the range 10 to the minus 12 electron volts. If I go towards supermassive black holes, 10 to the 6, 10 to the 10 solar masses, then we would be able to probe fields in the range of 10 to the minus 21-ish electron volts. And what does it correspond to in the particle physics literature is to think about wave-like dark matter candidates if you're in the range of 10 to the minus 20-ish electron volts, and QCD axion and axion-like particles in the range of 10 to the minus 10-ish electron volts. So there's a large range of possible particles. And what's really exciting is that we can actually use black holes to probe for these particles in a large range and independent of any coupling to the standard model, because these calculations only rely on the coupling to gravity. And that is interesting because if we say, oh, we want to look for dark matter, and we haven't really found anything yet in direct searches where we always rely on a certain coupling between the dark matter particle and the standard model, right? And at the same time, we do have these observations based on gravitational interactions. Moreover, we may be actually so unlucky that there is no or only very, very weak coupling to standard model particles. So probing through gravity only may be our best chance to find new answers to the dark matter problem. Okay, so this is why I think this is cool and interesting. Now, let's think about some of the phenomenology. And I want to highlight a paper by Freddie Hancock, one of my students here, which is not numerical relativity. So he used perturbation theory here, where he put a black hole in a bath of vector dark matter. And he has shown by finding solutions numerically that there can be an overdensity through accretion that really looks like a soliton around the black hole, similar to the profiles expected from some dark matter calculations. And what does that mean? So if I have a supermassive black hole of, say, 1 billion solar masses, then he found that the accretion of this field will enhance and increase the black hole mass faster than just accretion of standard model baryonic matter. and can create really an overdensity on accretion time scales that are of the order of 10 to the 8 years. So this is comparable to Bondi accretion of just ordinary baryonic matter. You can also ask what happens if we are in an overdense region that we can form through this amplification with a binary. And there is some work by Jamie Bamber and Yusa Orokocha, and more recently also by our group for massive scalar fields, where we have already seen that the interaction of the binary black hole with this overdense scalar or wave-like dark matter can yield a phase shift in the gravitational waveform. Okay, so this is two kind of scenarios that we might expect. So let me showcase some simulations for single black holes around embedded in scalar-like dark matter. And there's actually some very old simulation that I've done more than 10, well, yeah, now it's more than 10 years ago, where I put just a Gaussian wave packet around a rotating black hole and let it back react, and could find the late time solution. I should say a solution in quotation marks, because in this case, our field was slowly decaying. I allowed the field to have a complex frequency with an oscillation that was determined by the mass of the field. And the imaginary part of the frequency indicated that there was a very, very slow decay. And let me just play this animation. What you're seeing here is the equatorial plane. The black hole is rotating. The spin axis is pointing out of the plane. And what you've seen here is now the formation of this kind of scalar condensate, which is frame dragged along the black hole. Now you can go one step further and say, instead of just having what the group in Mexico called scalar wig, can go a step further and say, okay, let me actually put my black hole into a bars of scalar field. So the difference here is that now I fix my frequency to be a real, so I don't allow the field to decay, and I fix the frequency to be just a mass parameter. And what you get here are really hairy solutions. So this is a work by Katie Clough and her collaborators, and later followed up on by Jamie Bamber for rotating black holes, where you can see here the scalar field as a function of the distance of the radius. And in this case, the black hole was a Schwarzschild black hole. And what you will see here is that you can find standing wave solutions for different mass parameters. And here, green corresponds to a dimensionless mass parameter of 0.5, going to a mass parameter of 2 for blue. And the overall behavior is a decay here indicated as 1 over r to the 3/4. Okay, so these are the scalar bases, scalar hairs, and the work about the vector fields that I just showed from Freddie was really inspired here by Katie's work. So he reproduced, so he redid this kind of calculation perturbatively for Broca fields, and is now working on an extension to do this numerically. And then the last work I wanted to showcase is by the group in UT Austin, led by Jake Doherty, where it's not just about the massive scalar field, but they also allowed the scalar field to have a self-interaction term 5 to the 4, and looked at the accretion rates as a function of time. And the color coding here is a coupling parameter going from 2 times 10 to the minus 4 to 10 to the minus 3, and seeing an increase in the accretion rate early on in the evolution before it all settles down. Okay, so this is for a single black hole. What about binaries? I advertised this earlier, so this is work that we submitted recently, where we now want to consistently evolve a binary black hole surrounded by a scalar field cloud. One motivation I mentioned earlier, maybe we can probe for new particles, but at the same time, we can also use these simulations as a toy model to identify and quantify environmental effects during the merger, which I think becomes important when we want to do really high precision tests of gravity. Right? We want to make sure that we include all the physics that can be there before we talk about any modification to general relativity. Now, what we've done here is to extend the two-puncture Thorn in the Einstein Toolkit to allow for contribution from the massive scalar field, and we wanted to provide a non-trivial profile of the scalar field itself. So what we set up was a scalar field that goes like a Gaussian, again, Gaussian as our toy model of what a non-trivial profile could look like. And we set the momentum of the field to be 0. We derived the Hamiltonian momentum constraints for that. The nice thing is that with this choice, the momentum constraint is the same as in vacuum, so we can still use the Bowen-York solution for the extrinsic curvature as our solution, and the Hamiltonian constraint now is modified. We have the vacuum part, and then terms that go like the gradient of the scalar field squared plus a mass term. So far, so good. Then we went through the usual procedure using a conformal decomposition, using an ansatz for function initial data, where we say our conformal factor goes like the Berlinquist conformal factor plus a correction function. We assume asymptotic flatness, conformal flatness, and maximal slicing. So that means k is equal to 0. Wrote down our resulting differential equation, implemented that. And then we found that that became unstable. As we were increasing our resolution or our number of collocation points, we actually saw larger and larger noise coming in. So this whole whole solution was unstable. And we went back to the drawing board and said, wait a second. So let's think about what we want to do here. The Hamiltonian constraint essentially is an elliptic type equation. And one thing you might want to ask is whether this is actually a well-posed elliptic equation that gives unique solution. So this is, people usually hear me talking about well-posedness for hyperbolic problems, but in this case, we had to think about the ellipticity of the equation. And then if you go, for example, to Gauguin's lecture notes and references therein, you see that the condition for a well-posed elliptic equation is such that you have your Laplacian of your, say, perturbation minus a function times your perturbation, and this function needs to be larger than 0. Now let's take a look at the right-hand side here, where we have our linearized Hamiltonian constraint. We have our Laplacian minus some function times u. And then you see that this function has our standard a squared term, so this is fine, this is always positive, but we have a minus sign here for the gradient of the scalar field and its mass, and that can become so large that the overall term here becomes negative. And this is, I think, what we have seen. So what we did then is to conformally rescale the scalar field with a conformal factor. And if the exponent of the conformal factor is sufficiently small, we can get stable simulations, and they converge exponentially, as we see here, where we have the difference between our solution at a given resolution, number of collocation points n, versus our reference resolution, and we really see exponential decay here. So far, so good. So now we are ready to do simulations, and this is what we are seeing next, where we simulated binary black holes. Before we simulated this with Cheng and Giuseppe Ficara, we also extended our evolution, so space-time and scalar evolution code and wave extraction to 8th order finite differences. They both also took care to have low eccentricity orbits so that we can actually compare to LIGO data. So this is the ultimate goal in the future. So they spent quite some time to reduce the eccentricity below 10 to minus 3 roughly. And the simulation campaign was checking the mass ratio of the black hole between equal mass and the mass ratio 1 to 2. And we varied the mass parameter that I introduced earlier between 0.2 and 1. And the simulation that I'm going to show now is for simulation with mass ratio 1 to 2, mass parameter 0.2, and the color coding is the amplitude of the scalar field around the black hole. And we start with the Gaussian. And what you should be able to see now is that we start forming overdensities or peaks around each of the black holes that are orbiting and generating the scalar radiation that you see flowing out. And as the black holes eventually merge, the scalar field lingers around, decays very, very slowly, and because of the scalar radiation, it actually also, because of the scalar radiation that carries energy away, we also see a shift in the gravitational wave phase, in the gravitational wave emission. So I'm showing you just an inset on the merger of the dominant quadrupole mode of the Newman-Penrose scalar as a function of time. The black line here indicates a peak in the waveform for our vacuum reference simulation. And then for small mass parameters, mu 0.2 and 0.4, we indeed see this earlier merger due to additional energy emission from our scalar radiation. But we also see some delayed mergers, which we are still a bit puzzled by, and I don't have a conclusive answer yet why that is, if there's a dragging effect that slows down our in spiral. I think there must be, and I think that's something that we want to understand better in the future. Okay, so this is what I wanted to share with you about black holes and black hole mergers in a scalar dark matter environment. Next thing I want to talk about is binary black holes in modified gravity. And again, this is such a broad topic, and there's been a lot of really exciting work, so I will have to focus on just a few things. And I will focus only on black holes. My apologies to those of you in the audience. I know you're here who have done fantastic work on modified gravity for neutron stars, and actually shown some of the first effects of that. I will also focus on just what I would call quadratic gravity, where we have an extension of Einstein's theory involving terms that are Riemann squared, so quadratic in the curvature. The plots that I'm showing here are some of the earliest, are actually the earliest works on this topic. On the right-hand side here, work by Masha Okonkova and her collaborators on black hole mergers in either dynamical Chern-Simons gravity or what people call Gauss-Bonnet gravity. Don't worry about it. I'll show you the action in a second so you know what I'm talking about. And on the left-hand side, it's a snapshot of one of my simulations back in the day, where we also simulated binary black hole mergers in what's called scalar Gauss-Bonnet gravity. So what do I mean by that? What I mean by that is this Lagrangian here, where we say, okay, we have our Einstein-Hilbert term to start with, but now we want to extend that Lagrangian with higher curvature corrections, which might be interesting because you say, oh, if I want to find a theory that combines gravity at low energy scales and going toward the high energy UV limit, then you would expect to have these higher curvature corrections. Now, with that said, we don't have the full theory. We don't actually know what that is, but you can either take the low energy limit of some quantum gravity candidates, and they will give you something that looks like the Lagrangian I'm writing down here, or you can just build up a model from the bottom up to say, oh, let me just take a series expansion in curvature, where our Einstein-Hilbert term is the lowest order. And for both of these constructions, you would find as a next order in curvature squared, this Gauss-Bonnet term, where you have the Gauss-Bonnet invariant, which is a combination of the Riemann tensor squared, Ricci tensor squared, and Ricci scalar squared, such that your field equations are still second order in derivatives. Now, this by itself is a topological invariant, but if you couple this to a dynamical scalar field phi, then you actually do get modifications to your equations of motion. The other popular candidate that people have been thinking about is here on the right-hand side, where you say, let me now add what's called a Pontryagin eigendensity, or Riemann times the dual Riemann, and that is coupled to a pseudoscalar field or axion theta. And again, this term by itself wouldn't do anything, but if you couple it to a dynamical field, it actually does modify your equations. And most recently, people have also started looking at combining those two through a coupling function here, g of phi, And that's what is called axial gravity. The reason being that if you start from the string theory construction, taking the low energy limit reduced to 4 dimensions, you get in general both of these terms, where your scalar Gauss-Bonnet invariant is a parity even term, and your Pontryagin density is parity odd. So in the past, I think people have oftentimes looked at one or the other, and now we want to look at both of them together. Okay. So in order to do that, Chloe Richards, who is a graduate student here in my group, has implemented a parameterized numerical relativity code that allows you to evolve two scalar field model of gravity. And you're seeing the field equations here. So phi is a phi field that we saw on the previous slide. So this is a scalar. Theta is a pseudoscalar. We have their potentials here. And then you can have the coupling to the sourcing from the Gauss-Bonnet invariant for phi, and there is an additional term coupling both fields together. And likewise for theta, you have a derivative of the potential, the term that is essentially the Pontryagin density, dynamic Simons term, and the coupling between the two fields. And when I say parameterized, what I mean is that now you can choose through a simple parameter setting in your parameter file, which of these terms are you switching on? What is the form of your coupling function? So there are a few choices that you can have. Likewise, you can choose what kind of coupling you may want to have between your two fields and what the strength of that is. We also have a variety of choices for your initial data for both fields that go from just a zero field to a constant to a Gaussian to approximate solutions that people have found analytically in the literature. Now, I should also say, another advertisement, Chloe is another one of my students who is going to graduate next summer. So if you're looking for someone who is an expert on numerical relativity, in extensions of general relativity or new applications, I can highly recommend her. And actually, at the moment, she is going away from modified gravity and is using some of these models in the context of cosmology. So this code by itself really is very, very flexible. And if you want to take a look and download it, here's the QR code to do so. And I think
you have 5 minutes left.
Oh, fantastic. Yeah, perfect. Good. Yes, I think I just said this, that you can reduce to either one of these submodels very straightforwardly through simple parameter setting. And the next two slides, so I'm almost done. Next two slides will be about our recent results on simulations in axial gravity, where you have all of these terms switched on and the fields are also talking to each other. Okay, one more thing on that. You will see that I'm only writing down the scalar field equations because for this work that I'm showing you right now, the fields are not back reacting onto the metric. So the background metric is just described by general relativity. The reason being that for this orange term, dynamic Simons gravity, we still don't have a well-posed initial value formulation to do fully consistent simulations, including the metric. So here we are just focusing on the dynamics of both scalar and pseudoscalar fields in driven by a GR background. Okay, so with all of that said, let's look at single black holes. And let's think about what the black hole solutions could be. So we are taking our axial model. We are setting the coupling parameters in the allowed range, but quite large. So we set this to be a 0.1. I should also say that these coupling parameters are dimensionful. So alpha over m squared is a dimensionless quantity. And the background is Care in quasi-isotropic coordinates with a dimensionless spin of 0.9. And we will have both scalar fields initialized as 0. On the left-hand side, we will have the axion or theta field. On the right-hand side, we will have our dilaton or phi field. And the reason why I've drawn these sketches here is that analytical calculations where you assume the coupling to be small and the spin to be very small, they indicate that the leading order contribution to these hairs should be either the dipole that you're seeing here on the left for the axion or a kind of monopole here for the dilaton. Now let's see what happens as we evolve those and let these fields grow around black holes with a high spin. And what you're seeing, sorry, let me explain the plots first. What you're going to see here is the evolution of these fields in the ZX plane. So the spin axis of the black holes in the Z direction. So it's kind of looking at it from the side. And the color coding is the amplitude. So what you're seeing here is that within a relatively short time, less than 100 M here, you start forming two scalar hairs around your black holes. On the left-hand side here, the axion, nicely exhibiting this dipole shape. On the right-hand side, our dilaton, mostly a monopole, but you also see these kind of missing regions here. And that actually makes sense. If we now go back to the drawing board and look at the approximate solutions, the next to leading order term after the monopole is a quadrupole, L equal to M equals 0, and that comes with a minus sign. So we see here really how this is subtracted from our solution. So this is what we get at late times for high spins. And we all, well, I'm not showing you the curves in detail, but we also see how this high spin enhances our hair compared to, say, the approximate low spin solution. Okay, so now last one, if we say what happens if we put that in a binary. Again, our background is just a GR background. And for proof of principle simulation, we chose an equal mass, non-spinning black hole binary. And what we're seeing in the animation, again, on the left-hand side, let me just pause it for a second. On the left-hand side, the axion here, and on the right-hand side, the dilaton here. Well, the axion here on the left doesn't show anything. And that's not unexpected because the axion is only excited when you have spin. So we have non-spinning black holes, no evolution here until actually very late in the merger. Our dilaton here is present the entire time, and that's what you're, let me go back here. So that's what you're seeing here on the right-hand side. Again, we are showing the XZ plane, so side-facing the binary with our scalar charges now in spiraling and merging, and very late, just before the merger, we see the axion getting excited, and this is now the end state. So one of the things that I do not yet have for you are the full scalar waveforms, but what we would expect due to the additional 2 scalar radiation is that there would be a gravitational wave phase shift, and this is something that's ongoing with Chloe and former postdocs Alex Diemer and Deborah Ferguson. Okay, so now I'm coming to just my conclusion slide. So I hope I could convince you that there are really interesting applications of numerical relativity, not just beyond general relativity, but also beyond, say, the standard model of matter, or more generally, what I would call fundamental physics. And I talked about black holes and fundamental fields, where you can either use it to look for new types of particles or model environmental effects. And the typical effect on the waveform is this dephasing that one can try to look for. And in fact, Yoso Orokocha has a recent paper with LIGO data analysis colleagues where they tried to do that. And the last bit was about mergers in quadratic gravity and modified gravity series. So thank you very much. Before I take questions, can I make one more advertisement that might be interesting for the audience here? And that is the workshop that we organize every 2 years in Benasque in Spain. The next one is coming up in July, New Frontiers in Strong Gravity, the 4th iteration. Please consider coming, and I would be really happy to see many of you there. This is a picture from 2024 where we did that. So please consider coming, and thank you very much.
Thank you very much, Helvi, for the very nice talk.